Okay, nampak ke slides? All right, good. Okay, last Monday we have discussed about absorption of light and also absorption coefficient, right? So we have seen different levels of absorption coefficient, which affects the light absorption capability of a semiconductor material. And this is particularly important when we talk about optical devices or optoelectronic devices, which involves light absorption in order to function. For example, if you talk about solar cells, if you talk about photo detectors, so they depend on light absorption, or their sensitivity depends on their interaction with light, which then determines the operation of the devices. Okay, for example, solar cells, if you absorb less incident light, so it will result in low photocurrent from the solar cell. Okay, photocurrent here means current that's generated by the incident light. Okay, photocurrent. So that's why we need to know the absorption coefficient of our semiconductor material before we work on any particular semiconductor material to produce a device. Okay. So now let's move on to absorption depth. So absorption depth is given by the inverse of absorption coefficient. So absorption depth is actually the reciprocal of the absorption coefficient, or alpha to the power of -1, or 1 over alpha, if you like, right? So absorption depth is the distance. So what it means is it is the distance into the semiconductor material at which the light drops to 36% of its original intensity, okay, or alternately has dropped by a factor of 1 over E. Hold on, sorry. Okay, so if you press your calculator, so if you press 1 over E, then you're going to get about 36%. Okay, so when the intensity of the incident light drops to about 36%, so that shows the depth of absorption depth. Okay, the distance into the material at which the light drops to 36% of intensity. Okay, because when the incident light hits on the surface of your semiconductor material, as it travels through the semiconductor material, so as it goes through the material, the intensity of the light will be reduced and reduced and reduced accordingly. So the moment the reduction goes to the 36% of the original intensity, so that's called absorption depth, and also equals to 1 over E. So when the light is incident on the semiconductor material, high energy light or short wavelength light or high energy photons will be absorbed at the surface. Okay, so katalah you ada apa ni, this is your semiconductor material, and we know that our incident spectrum, if you talk about sun spectrum, for example, we know that our sun spectrum consists of UV portion and visible and also IR. Okay, some photons are from the UV, some photons are from the visible, and some photons are from the IR. Okay, so the photons in the UV region have the highest energy, and the photons in the visible have the middle energy, and the photons from the IR have the lowest energy. So when you move from UV to visible to IR, the photon energy decreases and the wavelength increases, because the wavelength is reciprocal of the photon energy, right? So upon the incidence, high energy light or high energy photons, which is equal to short wavelength, such as blue light, has a large absorption coefficient or alpha, and therefore they will be absorbed in a short distance of the surface. So that means high energy photons will be absorbed near the surface upon the incidence. Okay, While if you talk about red light, the long one, which is of low wavelength, will be absorbed less strongly. So the shortest energy will be absorbed at the surface, the middle energy will be absorbed in the middle of the bark, and the lowest energy will be absorbed at the back of your semiconductor material. For example, if you talk about a 300 micron of silicon wafer from the cross section, so the first few microns on the surface will absorb the blue light, and the central part of the silicon wafer will absorb the visible region. And as you go to near IR onwards to IR, the photons from these regions will be absorbed at the back of the silicon wafer. So we're going to see later on in the animation on how this works. So even after a few hundred micron, not all the light is absorbed in silicon. So this is determined by the magnitude of your absorption coefficient that we learned in our previous page. Okay, so if your alpha is high, so if the semiconductor materials alpha is high, so most of the light will be absorbed near the surface. So that means to be able to absorb most of the incident light, if you're talking about UV plus visible plus IR, high alpha semiconductor material only needs about a couple microns in order to completely absorb the incident light, because it has high alpha, and therefore most of the incident light will be absorbed by using a very thin layer of that particular semiconductor material. Whereas if you compare with semiconductor material like crystalline silicon with low alpha, it needs a relatively thick amount of material in order to completely absorb the same incident light. Okay, so that's the effect of high alpha and low alpha in terms of the physical thickness required in the semiconductor material in order to completely absorb light, right? So let me show you in the animation on PVCDROM website on how this actually works. So let me share the web. Absorption depth. Okay, hold on. Press the page. Sorry, that's another page. Oh no, on this one. Okay, hold on. Yeah, okay, this one. Okay, can you see the website on absorption depth now? Okay, good. Right, so you can come to this page later on and look at the notes later. Okay, absorption depth is under generation. So the notes up here is exactly what hold on, there are two students waiting in the lobby. Okay, the upper parts of the notes here is exactly what we discussed just now about the 36% reduction, and that equals 1 over E, and that is exactly the value of our absorption depth. So let's look at this animation. So we have two types of photons here. We have blue photons, which has short wavelength or high energy, and we also have at the same time red photons, which has long wavelength but low energy. Okay, so if you compare this, look at the absorption depth of both photons. So high energy blue photons are absorbed near the surface. So in the first few microns of the semiconductor material, if you look at this, it's more on the solar cell, but it's the very same principle. The blue photons disappear upon incidence at the surface, okay, due to its absorption at the surface. On the other hand, the red photons have to travel further into the depth of your semiconductor material before they can be absorbed, right? So let's look at that. The blue photons have disappeared already upon hitting the surface, but we still have red photons even towards the end of the thickness of our semiconductor material. So this is what it means. So just imagine if your semiconductor material is very thin, okay, this is considered relatively thick. For example, if your semiconductor material is only like here to here, only half or 1/3 of this original thickness, so that means the blue photons will be absorbed, but the red photons will not be absorbed. Okay, so if you relate back to the concept of reflection, transmission, and absorption that we learned before, so we're going to have our blue photons absorbed in the silicon, for example, but the red photons will not be absorbed because they just leak through the back of the semiconductor material because the thickness is not enough or the volume of the material is not enough. So in order for the semiconductor material to effectively absorb most of the light, in order for it to absorb most of the light, we need to have a relatively thick amount of semiconductor material, and that adds on cost. Okay, so if you talk about the physics, of course, you want to have as thick as possible crystalline silicon, for example, to ensure most of the incident photons absorbed, but it's just not practical in the real life because you need to have relatively thick amount of material that will add on costs to the manufacturing. So if you're talking about industry, manufacturers, solar cell, so we can't afford to have very thick silicon in order to ensure light absorption, a complete light absorption in the crystalline silicon wafer, because you will just add on a lot of costs. Okay, so what we have to do is a little bit of optics related tweaking or strategies to make sure that we can absorb all the incident photons using a relatively thin amount of material. It can be done. It's called light trapping. Pemerangkapan cahaya. You have to trap the light. You have to trap the photons inside the thin crystalline silicon in order to produce the enough current. So blue photon hilang maksudnya sudah diserap. Yes, exactly. So bila you tengok blue photon kat sini is gone, that means the photons are already absorbed by the material. Okay, so when you see the blue photons absorbed, you can still see red photons going to the back, right? Because blue photons are absorbed at the front and red photons are absorbed at the back. So kalau, for example, your thickness here is like half of this original thickness, there to there, so we will have our red photons leaving the silicon unabsorbed. Sebab kita tak ada, we don't have enough volume of material to be able to absorb the red photons at the back because it's now half or already 1/3 of the original thickness. So red photon akan keluar kat belakang and unharvested. Okay, unharvested. So if you talk about a semiconductor material like solar cell, which works on this principle, you want to absorb everything under the sunlight. Okay, so kita punya sunlight, if you look at our solar spectrum, we have UV, we have visible, and we have IR as well. So let me draw on a whiteboard for you to show this. Sorry, let me share the board. Okay, the board is loading. All right. Okay, let me share the whiteboard. Okay, can you see the whiteboard yang sudah diconteng sebelum ni? Nampak? Can you see the whiteboard? All right, good. So let me show you. Okay. So this is more on solar cell because it's a light absorbing device in order to produce electrical energy. So this is our solar spectrum. Okay, matahari kita, selalu kita tengok matahari, kita nampak matahari and that's it. So the solar spectrum, or the spectrum of sunlight from the sun, is exactly like this. So we have UV portion, we have visible portion, UV here, visible here, and IR here. Okay, and we have say your your solar cell, which is made of a PN junction. So say this one is crystalline silicon that we're talking about now, and we know that our blue photons are absorbed in the front, okay, and our red photons are absorbed at the back, okay. Blue photon, does it have short wavelength or high wavelength? Short, right? Okay, so the blue photon is coming from this short region, okay, visible. Like if you're talking about blue color, then it's probably somewhere there, okay, in the short wavelength region. If you look at the red, then it's probably somewhere here, okay. So we have this portion of UV, visible, and IR. So for you to have a good or a high efficiency solar cell, you want to absorb all of the incident light into your crystalline silicon solar cell. So you want to absorb UV, you want to absorb visible, and you want to absorb IR as well. Okay, so you want to absorb from the all of the incident spectrum, okay, all of the incident photons. But if your thickness is not enough, for example, okay, to be able to do that for crystalline silicon, since it has low alpha, so you need a very thick amount of material. Say this one is very thick. Example of a thick one, yeah. So if, but we cannot just do that. Say you might need, say, 500 micron, and that's like 5 times our hair thickness. And what we are using now in the industry for solar cell is about 180 micron of the wafer thickness. Okay, because we just can't afford to use so much of silicon because it adds more to the cost of the manufacturing. Say the industry can only afford to use this much of silicon, thin. So if you relate this back to the fundamental that we've learned just now, so blue photons will absorb, red photons may just leak through the back and not absorb because the thickness of the crystalline silicon is not enough to begin with, right? So in this case, we'll probably be able to absorb this portion of the spectrum only. If you use thin one, maybe you'll be able to absorb this portion of the spectrum, but until the red photons is no longer possible, okay? But if you use a thick one, a thick version, then maybe you'll be able to absorb the whole thing, okay? So the amount of light absorbed, so what you absorb in the solar cell will translate into your photocurrent. We call it short circuit current. We're going to learn it in the device later on, but anyway, this is the highest current produced in a solar cell. So light absorption is proportional to the short circuit current, or the highest current produced by the solar cell. So if your alpha is high, absorption coefficient is high, you can absorb most of the incident light, and you're gonna produce high photocurrent from your solar cell, and that will produce high efficiency solar cell as well. On the other hand, if your alpha is low, so that will result in low light absorption. Okay, that will result in low light absorption, and that will result in low photocurrent, and that will result in low efficiency. Okay, so by fundamental principle, if you want to get high efficiency, you have to use a relatively thick amount of crystalline silicon because it begins with a low absorption coefficient. Okay, so that's why when I explained last Monday, I think, for crystalline silicon, you need to use a very thick one, like 200 micron or so. Whereas for gallium arsenide, cadmium telluride, if you look at cadmium telluride solar cell manufactured by First Solar, so they only need about 2 to 5 micron of the cadmium telluride material in order to completely absorb the incident light, whereas you need, say, 300 micron for silicon or 200 micron for silicon. So that's like 100 times or 200 times lower in terms of the material consumption. So this is the, the techno-economic reasons, techno-economic factors that need to be considered when we talk about manufacturing of our semiconductor device. So at this point, when you learn about the physics, we only learn about the physics and the ideals, okay, the ideals. Tapi bila kita nak apply, when we talk about manufacturing later on, how do we use the physics in order to manufacture, to fabricate the actual semiconductor devices? Other factors that are beyond physics will come into the picture and play a big role in the decision making. So normally when you talk about this, we can summarize all these factors and you can call that as techno-economic. So this is beyond physics, okay? Techno-economic factors. So this is a bit on the manufacturing already, but anyway, since we've been talking about the technology, well, all this while we have been considering this, the physics, the technology, the capability of material, band gap, blah, 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 blah. But when we talk about manufacturing, this one plays a bigger role, the economic of it. Is it economic? Is it commercially viable? Do we have a market for it? Do we have enough volume for it? Do we have enough demand for it? Okay, so combine them together, so it will form a very, what I call, robust knowledge, I would say, robust knowledge in order for you to make decision when you talk about manufacturing of the technology. So it's techno-economic. So now we learn the ideals, but when we want to implement the technology into the real scale, mass production, for example, then this will come into consideration, okay? So I'll go back to the notes. So is it okay so far? Is it clear on the high energy photons absorption, rate photons, thickness required, and stuff like that? Is it okay so far? You can see, right, the economic factor coming into play now, right? So the techno part is the volume, absorption coefficient, alpha, and stuff like that. But when you talk about the economic part, that will be the amount of material, cost added to the technology, and blah, 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 blah. Because when you talk about solar technology, the benchmark that we need to use is US, let me write it down here, USD per watt, okay? So this is the benchmark that you need to use in order to compare technology costs for, say, crystalline silicon solar cell versus cadmium telluride solar cell versus gallium arsenide solar cell versus other whatever solar cell. So it boils down to US dollar per watt. So that means how much do you spend in order to get that technology, which is US dollar, versus or normalized over wattage produced from the solar cell. How much power can you extract from the solar cell? So how much you need to spend on the technology to fabricate the technology, and how much power can you extract? So that will give you dollar per watt. So this is a golden benchmark that we need to use in order to compare whether technology 1 is better than 2, 2 is better than 3, or which is better than which, and whether or not the emerging technologies are viable for mass production. So the number is called, the metric is called dollar per watt, right? So if your new technology is fantastic, it can absorb more light, blah, 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 but end of the day, if the dollar per watt is much higher than the current technology in the market, no point. It's not going to go into the market. It doesn't matter if it's fancy enough or it can absorb more stuff, it can do more fancy things. But if the dollar per watt is not promising, no, it won't go into the market. Okay? So the equation will be slightly different and it's going to be more comprehensive beyond the physics. Right, so let me go back to the notes now to continue. Okay, nampak kan slides? I reshare the slides. Okay, nampak? All right, cool. So that's absorption depth, it's clear. So the depth required for the intensity of light to drop from 100%, which is the source of the incident light, to 36%. So why 36%? Because most of the incident light, or not most, perhaps the blue part and some other visible photons are already absorbed. So that makes intensity reduces to about 36%. Okay, so that's why only 36% is left if you compare to the original intensity of the incident light. Okay, generation rate. Generation G, you have learned this one before briefly, is the greatest at the surface of the material where the majority of the light is absorbed. So when we talk about generation, we are talking about generation of electron hole pairs. Okay, remember last time when we talked about three cases of photon energy versus band gap? Remember, what are the three cases when you have incident photons incident on your semiconductor? Three cases will happen. Okay, either one of the three. What are the three? Remember, case number one is when your photon energy is what? Compared to the band gap. Let's recap before we talk about generation, because they are related to each other. What happens to the case number one? EPH is blah 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 compared to band gap. EPH versus EG. Anyone? Let me call some names. Alia Nasrin. Alia, what's the case number one? Come on. Alia, you're on? How about Akila? Okay. Go said equals, smaller, larger. Okay. All the three cases already said. Okay, go. How about case number one? What if the EPH is smaller than EG? What happens? What happens when EPH is smaller than EG? Case number one. What happens next? Go, you can unmute yourself, I can write down. Because it's related to generation, so we need to be clear on that first. Or anyone else? Derwina? What happens when EPH? Okay, Rafai said photon behave as transparent. Okay, good. Photon behave as transparent. So that means what happens to the photon? Will it be absorbed? Rafai, you can elaborate a little bit. Will the photons be absorbed by the material? Okay, no absorption. So no light absorption. Okay. So when there's no light absorption, is there any transition of electron from valence band to conduction band? No. Good. Right. So photon is behave as they are transparent, and there's no light absorption, and therefore when there's no light absorption, there's no transition of valence electron from valence band to conduction band. Photon akan just pass through the semiconductor material, and most of the light, or you can say that 100% of the light will be leaking through the back of the semiconductor material unabsorbed at all. Okay, so that's case number one. How about case number two? EPH equals to EG. So let's recap the very same thing, but what happens now? Do we have any absorption? Yes, Akila said yes. Okay, so the light is absorbed. As a result, do we have any transition of valence electron into the conduction band? Yes, right? Okay, yes. Because kita kena ada conservation of energy kan. So you absorb the energy from the photon as a result. So that's the conservation part. As a result, the energy is used to excite the valence band electrons into the conduction band, or they are called excited now. So they can do the conduction in the solar cell, for example. So when the light is absorbed and the valence electron is excited into conduction band, now if you probe your current voltage curve on your solar cell, for example, you can see the curve. Okay, you can see the current, you can see the voltage, because now it's operating as a solar cell because the light is absorbed and the energy is converted into electrical energy. And as a result, you can see a curve, okay, current voltage characteristic curve on the screen. Right, so how about case number 3, when EPH is more than EG? Okay, EPH more than EG. Do we have the light absorbed? Do we have any light absorption here? Case number 3? Yes, okay, so EPH is more than EG, so we have light absorption. Okay, do we have a valence electron transition into conduction band? Good, do we have it? Do we also have transition? Yes. So then what's the difference between case number 3 and case number 2? If both cases show electron transition, then what's the difference between case number 2, where both energies are equal, and case number 3, where photon energy is more than the band gap energy? Yes, the presence of excess energy. Okay. Case number 2 tadi, EPH equals to EG. Case number 3, EPH more than EG. So the difference is in the sign there, right? One is equals to and one is more than. When you talk about more than, so that means the energy that you supplied is more than what you actually required, okay? So more than the energy required. So as a result, you're going to have valence electron excited further up, not just towards the band edge, but further up into the conduction band. And you're going to have the excess energy, the energy difference between EPH minus EG, the difference between the two energy levels, versus the EG required. Okay, so this is the excess energy, and we're going to have thermalization for case number 3. And the excited electrons will thermalize back to conduction band H. So that is the difference, and energy is wasted. Okay, so that's why. So actually, if you talk about the energy of these 3 cases, EPH less than EG, equals to EG, more than EG, the ideal case is only when the EPH is equal to EG, right? So that's the ideal case, but that's just not possible because we have a spectrum of sunlight. It's not like a monochromatic wavelength, right? It's not a single wavelength. We have UV, we have visible, and we have IR to do the same, to do different roles on the Earth. Okay, untuk dia masing-masing punya region ada dia punya own peranan lah, diciptakan oleh Tuhan untuk memainkan peranan masing-masing. UV ada dia punya own role, and visible ada dia punya own role, and IR has its own role as well. So, but we know that the ideal case is when EPH is equal to EG. Exactly. At the same time, we know that EPH more than EG can also give us some electricity from the solar cell, but we're gonna need to suffer from the thermalization effect. So that's why if you talk about recent generation of technology in solar cell, it's also called hot electron technology. Hot electron, hot electron ni electron yang excited to higher energy level than the required energy level. Maknanya dia pergi atas sangat, and this excess energy will be thermalized anyway. So we cannot harvest the excess energy. So what we can do is we need to tap the energy before thermalization. Okay, so you need to capture the energy before it's lost due to thermalization. And this is called hot electron punya research. Okay, dalam solar cell, it is being done as well. So kalau ibu minat, you can just search on it and see hot electron for solar cell. You can see this. In order for us to go beyond the theoretical limit of the current technology. Okay, so to relate back to generation, so this is the thing: when you absorb the light, you want to generate electron hole pairs. So generation of electron hole pairs, we've discussed this now, where we have EPH equals to EG, we can generate electron hole pairs, and also when we have EPH more than EG, we can also generate electron hole pairs at the expense of thermalization effect. So this is exactly the G that we're talking about, the generation. And this generation is the greatest at the surface because most of the incident photons are absorbed near the surface. Okay. So G rate or generation rate gives the number of electrons generated at each point in the device due to absorption of the photons. Right? Absorption of photons result in generation of electron hole pairs. If there is no absorption of photons, there will not be any generation of electron hole pairs. As simple as that. So for case number 1, there will not be any generation of electron hole pairs because photons are transparent to the material. Okay, due to the lower energy when you compare to the band gap. All right, so let me finish this off in the next few minutes. So neglecting reflection, if you assume zero reflection, for example, the amount of light which is absorbed by a semiconductor material depends on absorption coefficient. So recall that the capability of the light absorption is depending on the alpha value, right? So the higher the value of alpha, the easier or the higher the capability of the material to absorb the light. If your alpha is lower, then the capability will be lower as well, right? So this depends on, okay, the amount of light which is absorbed depends on alpha and the thickness. Okay, alpha and thickness affect the amount of light absorbed. Okay, tadi kita tengok kan, blue photons versus red photons, thick condition versus thin condition. So that shows one dependence already, the thickness. The intensity of the light at any point in the device can be calculated according to the below equation. I equals to I naught exponential of negative alpha times x, where alpha is the absorption coefficient we've discussed before this, x is the depth into the device, okay, x is the depth, the cross section here, the cross section of this semiconductor material. So the thicker the crystalline silicon wafer, for example, the x will be different, bigger. If you use a very thin layer of crystalline silicon, the x will be smaller. And okay, and I naught is the light intensity at the top surface upon the incidence on the surface. Okay, so the moment it penetrates into the silicon, crystalline silicon, you're going to need to know what's the intensity of the light at a specific depth inside. So differentiating from this equation, differentiating I will give you G at any point in the device. Remember, I can be calculated at any point in the device. So if you differentiate this, you're going to have G also at any point in the device. And that will be given by G equals to alpha times N naught exponential of negative absorption coefficient times that as well, where N naught is the flux at the surface. So we've discussed before this about the flux and generation rate. Okay, remember I think last class, okay, the flux equation, yeah, F naught equals to Fx equal to F naught exponential component. So in this equation, alpha is absorption coefficient as well, and x is the depth into the material. So if you plot this equation into a graphical representation, you're going to have a graph like this. So generation rate on the y-axis versus depth on the x-axis. So if you want to draw this as your silicon wafer, for example, so that will be the photons incident on the surface at naught position, and not the kat sini ya, kalau n naught kat sini ya, kat surface, but not means the starting point. Okay, so the moment it goes through, so the intensity, so this, if you plot this on the x, if photon jatuh kat sini, so this one surface of the silicon, okay, which is here, which is there. So going into the silicon is going through this, left to right, okay? Left to right. So the deeper your silicon, say if your silicon is 300 micron, in this case, so you're going to see the intensity of the light down to up to 300 micron thickness, okay? So generation rate is like this, exponential shape. It reduces exponentially. So generation rate will be the highest at the surface because most of the photons absorb at the surface, particularly the blue photons, and you need relatively thick amount of material in order to absorb most of the light. Okay, of the light. You can actually go back here to the absorption depth. Kalau you nak tahu, you can actually, okay, let me just go back to the absorption depth before I finish. We're going to cover the relaxation in the next class. Let me show you something on the website. Absorption depth. Okay, let me show you again. Okay, nampak kan website? Share ini the very same websites now. Nampak kan? Yeah, can you see? All right, good. So the depth here is, oh, we don't have it here. Absorption coefficient. Saya buka ni. What's the depth? It doesn't show here. Hold on. This is coefficient. Let me see this. Okay. So you can come here. You can click just now the optical properties of silicon, and that will bring you to this page, and you can see here the whole thing. Okay. So first is the absorption coefficient of silicon, which was discussed last time when we compared gallium arsenide, gallium telluride, crystalline silicon, and whatnot. So this is the alpha value of silicon. So we have learned that absorption depth is the inverse, right? Is the inverse of absorption coefficient. So absorption depth is 1 over alpha. So when you inverse this value on the left, on the y-axis, you're going to get this curve. Okay, absorption depth in centimeter. Okay, this one, remember, absorption coefficient is in cm minus 1. So when you invert, you're going to have centimeter. And from this, you can see the depth required is on the y-axis, and the wavelength of the light is on the x-axis. So you can tell here, kalau you nak tahu, for example, photons of certain wavelength, how deep is required for that particular photon to be absorbed. For example, if you go down to, okay, if you go to 800 nanometer here in the central part, more or less, of your x-axis, so that means, okay, your y-axis here, the depth is plotted either in cm on the left or in meter on the right, but they are the same thing, cuma different unit, yeah. So if you look at it at the 800 nanometer, so see if you have photons of 800 nanometer wavelength, so that means it's going to need about how much? 1 times 10 to the 5 micron. How much is 1 times 10 to the 5 micron? How thick is 1 times 10 to the 5, 10 to the minus 5 meter? Berapa micron? If you want to convert into micron, berapa micron? So look at this, 800, go to the right there, and that equals to 1 times 10 to the minus 5. So berapa micron tu, if you convert into micron? Betul ke 001 micron? So look at the unit there on the secondary y-axis, it's in meter, right? So 1 times 10 to the 5, 10 to the minus 5 meters. So kalau you convert that into micron, jadi berapa? Come on. Berapa micron tu? 1 times 10 to the 5 meter, tukar kepada minus 6 kan? Micron yang minus 6, right? So that equals to what? Anyone? Come on, simple conversion ni. Berapa micron, anyone? Come on. 10 kuasa 11. Really? Are you sure? Okay, if you want to convert, 10 micron, right? 10 micron, right? 10 times 10 to the If you put that into writing, 10 equal, if you write 10 micron is equal to 10 times 10 to the minus 6 meter, right? And that is also equal to 1 times 10 to the minus 5, isn't it? So 800 nanometer requires about 10 micron of crystalline silicon to be absorbed. Maknanya kalau you ada, let's say if you're using 10 micron of crystalline silicon, you can only absorb from the UV, from the short wavelength up to 800 only. Okay, you cannot absorb photon wavelength above 800 because the thickness is not enough. Okay, maknanya photons above 800 nanometer will be leaking through the back of your crystalline silicon because the thickness is not enough. Okay, so you can use this absorption depth curve in order to predict how much, or in order to see how much do you need in order to absorb what sort of wavelength. Okay, so you can start from the front last, but you remember when we talk about UV upper band gap absorption, if EPH more than EG, right? So katalah we're talking about photon energy more than or equal to 1.12 for crystalline silicon. So that means all the photons with energy of less than 1.12 will be absorbed by the crystalline silicon. Okay. No, higher than, right? Higher than the energy of 1.12. Okay. Any energy above 1.12 electron volt will be absorbed. Photon yang ada energy above 1.12 will be absorbed. Photon yang ada energy below 1.12 will not be absorbed and will be transparent. So that means if you translate that energy electron volt, the photon energy, into wavelength, so that means since 1.12 is equal to 1100 nanometer on the y-axis now, so here if you convert photon energy to wavelength, so 1.12 is somewhere here, so that means all the wavelength, all the photons with the wavelength below 1100 nanometer will be absorbed because they have higher energy than 1.12 electron volt. So that means if you have 800 just now, like our previous example, all the photons on the left hand side will be absorbed until 800 nanometer only because your thickness is only 10 micron. Okay, so if you work with thickness of material, and in order to quantify light absorption, you can come back to the absorption depth curve of your semiconductor material. If you don't have the absorption depth, you can go back to the alpha of that particular material, and you just invert the alpha, 1 over alpha, then you're going to have this depth, and then you can plot like this in cm or in meter as well, and then you can correlate with the thickness required in order for you to absorb certain wavelength of the photons from your incident light. Okay, so that's how you use this curve. Okay, it's very useful, it's very simple, but then it can be used for many different purposes. So one of them is to predict the thickness required in order for you to absorb that particular photon wavelength. So is it clear on the use of the curve just now? Is it okay? Senang aja kan? You invert the alpha and you get the depth, and then you ask yourself, what photon wavelength do you want to absorb? And therefore, what sort of thickness do I need? And you go to the curve, the absorption depth curve, and see at that particular wavelength, what is the thickness required on the y-axis, and that is the minimum thickness for you to have in order to absorb that particular wavelength, or else you won't be able to absorb completely. Okay, is it okay? Paham ke? Okay kan, paham kan? Good. Right, so that's it for today. I'll see you again tomorrow then. Okay, tomorrow. Hey, sorry, today's what? Say lost day lah. Today Wednesday or Thursday? Today's Wednesday, sorry. So tomorrow will be 10 a.m. then. Yeah, lost count already. Thank you very much. Tomorrow the class, yes. Confused kalau hari ni Thursday, then tomorrow will not be any class already, right? So, yeah, okay then. So I'll see you tomorrow, inshallah. Bye-bye, take care. Assalamualaikum.